Imagine, for a moment, a cage. Not a cage of iron bars and cold steel, but a cage of pure, breathtaking intellectual light. A structure so elegant, so perfectly formed that it explained the dance of planets, the birth of stars, and the very fabric of reality. It's a cage built from the most profound insights a single human mind has ever conceived. We have lived within this beautiful cage for over a century. We have grown comfortable here, mapping its every corner, marveling at its robust and intricate design. We call this magnificent structure Einstein's theory of relativity. It is, without question, one of the greatest achievements of human civilization. It has given us GPS, nuclear energy, and a vision of the cosmos that is both majestic and deeply strange. It tells us that space and time are not separate, but are woven together into a single dynamic fabric, space-time. It tells us that gravity is not a force, but the curvature of this fabric, a gentle warping caused by the presence of mass and energy. A planet orbiting a star is not being pulled by an invisible rope. It is simply following the straightest possible path through a curved, four-dimensional landscape. It is poetry. It is mathematics. It is truth. But what if it's not the whole truth? What if this beautiful cage, for all its splendor, has bars? What if by defining our universe so perfectly it also limits our vision, preventing us from seeing what lies beyond? This is not heresy. This is the very soul of science. And today, we stand at the precipice, looking through the bars of this cage, and we see inconsistencies, shadows, ghosts in the machine that tell us a profound and unsettling story, the story of how Einstein's perfect universe is beginning to unravel. This is the story of the Einstein Cage, and it is a call for a new physics. To challenge a giant, you must first acknowledge his stature. Albert Einstein was not just a physicist, he was a prophet of the cosmos. In 1905, with his special theory of relativity, he dismantled centuries of scientific dogma. He declared that the speed of light in a vacuum is an absolute constant, a universal speed limit that nothing can exceed. The consequence of this simple, radical idea was earth-shattering. Time itself, he proved, is not absolute. It slows down for an object in motion relative to an observer. Lengths contract. Mass increases. He wove space and time together, and in doing so, he gave us the most famous equation in history, E equal to mc2. Energy equals mass times the speed of light squared, an equation that holds the secret of the stars and the power of the atom. It was a revolution. But he wasn't done. For 10 more years, he wrestled with gravity. Newton's vision of gravity as an instantaneous force acting at a distance bothered him. It violated his own universal speed limit. The result of his struggle was the general theory of relativity, a masterpiece that describes the universe on the grandest of scales. It predicted that starlight would bend as it passed the sun, a prediction confirmed in 1919, making him a global icon overnight. It predicted black holes, objects with gravity so immense that not even light can escape. It predicted the expansion of the universe itself. For 100 years, we have put general relativity to the test, and it has passed every single one with flying colors. It is, by all measures, the most successful scientific theory ever devised. And that is precisely what makes the cracks now appearing in its foundation so terrifying and so exhilarating. The first and deepest crack comes from a world that Einstein himself helped to create, yet never truly accepted, the world of quantum mechanics. Physics, in the 20th century, split into two great kingdoms. General relativity became the undisputed king of the very large stars, galaxies, the universe itself. It's a world of smooth curves, deterministic laws, and elegant geometry. Quantum mechanics, on the other hand, became the lord of the very small atoms, electrons, and the subatomic zoo of particles. It is a bizarre and chaotic kingdom, ruled not by certainty but by probability. In the quantum world, a particle can be in multiple places at once until you measure it. It's a world of jittery, unpredictable quantum leaps, not smooth, flowing trajectories. For decades, these two kings have ruled their domains in peace, because their paths rarely crossed. But in the most extreme places in the universe, the kingdoms collide, and the result is a catastrophic failure of law and order. Think of a black hole. At its heart, general relativity predicts a singularity, a point of infinite density and zero volume, where a colossal mass is crushed into an impossibly small space. Here, the gravity is infinitely strong, the curvature of space-time infinitely sharp. Einstein's equations, the beautiful laws that describe the cosmos, simply break. They produce nonsensical answers, infinities that tell us our theory has hit a wall. But a singularity is also an incredibly massive object in a tiny, tiny space. It is where the kingdom of the large and the kingdom of the small become one, And so, to truly understand what a singularity is, we need a theory that can speak both languages. We need a theory of quantum gravity. We don't have one. General relativity and quantum mechanics give us completely different, incompatible descriptions. It's like trying to read a book where all the even-numbered pages are written in Shakespearean English and all the odd-numbered pages are in binary code. They are both descriptive, but they don't speak to each other. The same problem occurs at the other extreme of existence, the Big Bang. Our understanding of the universe's birth begins a fraction of a second after the initial event, because at the moment of creation itself, the entire observable universe was packed into a space smaller than an atom. Again, the large and the small were one. And again, Einstein's theory fails us. The two pillars of modern physics are mutually exclusive at the very points they are most needed. This isn't a minor disagreement. It is a fundamental contradiction at the heart of our understanding of reality. The second crack in the cage is not hidden in the quantum realm or at the beginning of time. It is all around us on the largest possible scales. It is silent, it is invisible, and it makes up 95% of the entire universe. We call it dark matter and dark energy. According to general relativity, we should be able to measure the mass of a galaxy by the speed of its rotation. The faster the stars on the outer edges are moving, the more mass there must be at the center, providing the gravitational glue to hold them in orbit. When we did this, starting with the astronomer Vera Rubin in the 1970s, we found something staggering. The stars were moving far too quickly. So quickly, in fact, that the galaxies should be flying apart. The visible matter of the stars, the gas, the dust wasn't nearly enough to account for the gravity required. To make Einstein's equations work, there had to be something else, a huge, invisible halo of something. We called it dark matter. We can't see it. It doesn't interact with light or any other form of radiation. It doesn't seem to interact with normal matter in any way, except through gravity. We know it's there because we can see its gravitational effects, bending the light from distant galaxies in a phenomenon called gravitational lensing. But we have no idea what it is. It is, in essence, a ghost in Einstein's machine. It's a fudge factor we had to invent to save the theory. And it gets stranger. In the late 1990s, two teams of astronomers were studying distant supernovae to measure the rate at which the universe's expansion was slowing down. Everyone assumed gravity was putting the brakes on the cosmic expansion that began with the Big Bang. They were trying to measure the deceleration. To their utter astonishment, they found the exact opposite. The expansion of the universe is not slowing down. It's speeding up. Something is actively pushing space-time apart, acting like a form of anti-gravity. To account for this in Einstein's equations, we had to add another placeholder, another mysterious entity. We call it dark energy. And the amount of this energy needed is immense. When you add it all up, the ordinary matter we see and interact with every day, the stuff that makes up you, me, the planets, the stars, accounts for a mere 5% of the universe. About 27% is the mysterious dark matter holding galaxies together, and a whopping 68% is the even more mysterious dark energy pushing everything apart. Think about that. Our most successful theory of the cosmos is completely blind to 95% of its contents. Is it possible that dark matter and dark energy are real undiscovered substances? Yes. But is it also possible that they are phantoms? Phantoms born from the fact that Einstein's theory of gravity itself is incomplete and starts to break down on galactic and cosmological scales? Some physicists think so. They propose that we don't need dark matter, but rather a modified theory of gravity, a MOND or modified Newtonian dynamics, that behaves differently at very low acceleration. This is a radical idea, but it highlights the central problem. We are clinging to a theory whose equations only balance if we invent vast quantities of stuff we can't detect or explain. The third crack in the cage is perhaps the most personal because it concerns something we all experience yet cannot define: the passage of time. In Einstein's universe, time is relative. It is the fourth dimension, inextricably linked with the three dimensions of space. One consequence of this block universe model is that the past, present, and future are all equally real, all existing simultaneously within the four-dimensional block of space-time. Your birth, you reading this sentence, and your death are all just different coordinates in space-time. The flow of time, that feeling of moving from a fixed past into an unknown future, is, according to this view, a deeply powerful human illusion. But this is completely at odds with our experience, and, more importantly, it clashes with quantum mechanics. In the quantum world, the future is not predetermined. It is a landscape of probabilities. The act of measurement seems to force one of these possibilities to become the concrete, real present. There is an arrow of time baked into the quantum process that simply doesn't exist in relativity. This is known as the problem of time. For relativity, time is a geometric coordinate. For quantum theory, it is a universal ticking clock against which events unfold. They can't both be right. Which is it? Is time an illusion? Or is its passage a fundamental feature of reality? Until we can answer that, we have two warring conceptions of the very medium of our existence. Finally, there is Einstein's most famous decree, the universal speed limit. Nothing, he said, can travel faster than the speed of light. It is the bedrock of causality. If you could violate it, you could travel back in time and create paradoxes. Yet, the quantum world offers a tantalizing, spooky challenge. It's called quantum entanglement. You can create two particles, say two photons, that are intrinsically linked. They fly off in opposite directions, potentially across the entire universe. The strange thing is, certain properties of these particles, like their spin, remain in an undecided state until one is measured. The moment you measure the spin of photon A, you instantaneously know the spin of photon B, no matter how far away it is. It's as if information, the result of the measurement, has traveled between them faster than light. Einstein famously hated this, calling it spooky action at a distance. Now, to be clear, every experiment has shown that you cannot use this phenomenon to send a useful message faster than light. The outcome of the measurement on photon A is random, so you can't control the outcome for photon B to send a code, for instance. Causality is preserved, but the correlation is instantaneous. It suggests that on some deep, fundamental level, the universe is non-local. It suggests that the two particles are not separate entities, but are somehow still connected as part of a single system, regardless of the spatial distance between them. This profound interconnectedness is something that doesn't sit comfortably within the geometric, local framework of general relativity. It's another hint that there is a deeper layer to reality that Einstein's theory does not capture. So where does this leave us? We are here, inside this magnificent, shimmering cage. We have found cracks, the irreconcilable war between the macro and the micro, the ghosts of dark matter and dark energy that make up 95% of reality, a deep confusion over the nature of time itself, and spooky, faster-than-light connections that defy our classical intuition. To point these things out is not to diminish the legacy of Einstein, it is to honor it. Einstein himself was a revolutionary who overthrew a 200-year-old Newtonian paradigm because he saw cracks in its facade. He would not have wanted us to turn his theories into dogma. He would have wanted us to test them to their breaking point. We have found that breaking point. The call for a new physics is now echoing through the halls of science. Physicists are working on candidates for a theory of everything. Ideas like string theory, which posits that all particles are just vibrations of tiny, unimaginable strings, and that promises to unite gravity and the quantum world, or loop quantum gravity, which suggests that space-time itself is not smooth but is made of discrete, indivisible quantum chunks. These are monumental, almost impossibly difficult tasks. We may not solve them in our lifetime, but the quest has begun. Escaping the Einstein Cage is the great scientific adventure of the 21st century. It is a journey not of disrespect, but of evolution. It is about understanding that every great theory is a stepping stone, not a final destination. And as we push against the bars of this beautiful cage, we do so with the same spirit of relentless curiosity that led Einstein to build it in the first place, reaching for a new, deeper, and more wondrous vision of the cosmos that awaits us on the other side.